Today, the computer components market is very hot. The RTX 3060 consumes more than 200 watts. The Ryzen 5 heats up to 100 degrees under a tower cooler. Not even speaking about top-end hardware. If you haven't got some liquid nitrogen on your hands, don't even think about overclocking. But I'll tell you what, all these watts are bloated, just to squeeze a couple more % of performance out of your hardware. Huge power consumption of modern chips is yet another result of marketing tricks. But we can play their game the other way around. In just a couple of clicks, we can not only reduce power consumption, but also increase performance. As you have already guessed, today we're talking about lowering the voltage in your system, also known as undervolting. For this, we got a PC with a new Intel CPU, a socket with a screen, a watt meter, and a small thermal imager just like that. You will not need any of this. All you need is attention and understanding of the basics. We'll try to make it as clear and visual as possible. In my main PC, the 7600X is of course undervolted too, and the GPU has now been adjusted as well. This is MK. Today we're trying to win the silicon lottery. Let's go. The test bench this time was provided by MSI. This is a pre-built MPG Infinite X2 computer, and this is just the perfect test subject for our undervolting ventures. Here we have a 300-watt RTX 4080, the MSI Ventus version, and under the 2-section water cooler is sitting one of the best processors for the LGA 1700 socket, the i7-13700KF. This CPU has got a hot temper. It can consume more than 250 watts, but most importantly, look at the board. Have you ever seen so many VRM phases without a heatsink? I haven't. For our experiment, it's even better. It will be easier to take temperatures with our thermal imager. Although this is an OEM solution, it is based around a top-end Z690 chipset, so we're not limited in any way. We can overclock both the processor and memory, which in this case, by the way, is the most basic. 2 grain sticks by Samsung, 16GB DDR5 at 4800. When looking at it from the other side, we got 3 surprises at once. First of all, yes, the cable management is good, no doubt about it. If I were to build it myself, I wouldn't try that hard. Secondly, keen-eyed viewers probably have already noticed traces of a sticky substance on the back of the board. The repairman would see that this is flux, unwashed at the factory. MSI told us that they use a non-washing flux which they don't clean in order not to harm the environment. So these traces do not seem to be causing any issues except for aesthetics. And the third surprise is an 850-watt power supply unit in a pre-built PC, when according to official specifications, which are written with a margin, for the RTX 4080 a 750-watt solution is enough. A good OEM FSP is used, with gold certificate, active PFC and AC/DC, which means the highway to hell is cancelled. And it seems that even this is too much. Soon we will find out how much. But as crypto miners say, there is no such thing as too powerful a PSU. That's basically all you need to know. Now let's remove all the limits and see what happens. DDR5 at 4800 MHz is laughable. A Z690 board, and actually any board except the H610, makes it possible to overclock memory to 5600 MHz with just a tweak in the BIOS, which gives up to 80 GB per second of throughput. Not record-breaking, but it makes no sense to overclock it even further. The performance difference is marginal, for the Core i7's cache memory is quite capacious. We gave the CPU a full carte blanche too, changing the factory limit from 125 to 300 watts. After all, it is a top-end water-cooled gaming PC, and the water cooling didn't help. Yes, that's a modern CPU for you. In the Cinebench test, the i7-13700K at peak consumed more than 250 watts, constantly throttling at 100 degrees. Only a 3-section water cooling system can handle such TDP, and even then, not any will do. In our case, thermal throttling turned out to be quite serious. The peak cores were boosted to 4.8 GHz, while the maximum frequency is 5.3. Whether undervolting can help return the lost half a gigahertz, we'll see later. But for now, let's also note another unpleasant result of the processor's huge power consumption: the heating of the VRM. Passing through more than 100 amperes of current, the MOSFETs heat up a lot. In our case, up to 80 degrees after half an hour in Cinebench. These temperatures are quite high, but not yet critical. I expected much higher temperatures from a board without heatsinks on the VRM, but then apparently their number and quality saves the day. Therefore, in our case, the bottleneck is the water cooling system, which prevents the processor from reaching its full potential. This is also noticeable in other demanding tests. In the White Cruncher test, our 24-thread CPU was able to compute 2.5 million digits of pi after the decimal point in 1 minute and 6 seconds, boosting only to 4.8 GHz. But in simpler tasks, there are no overheating and thermal throttling issues. In the 7-zip archiver under full load, the frequencies of the P cores maintained above 5.2 GHz, which made it possible to score 150 GIPS. In the CPU-Z quick test, the result is also good. More than 1200 points. This is the level of the 16-core Ryzen 9 5950X of the previous generation. Speaking of the gaming benchmark 3D Mark times Pi, it was not a problem at all. The maximum 5.3 GHz and an impressive 19.5 thousand scores. So the verdict for our Core i7 is quite unambiguous. It is very hot, and undervolting is a must for it. As for the huge RTX 4080, the superposition test even in 8K is too simple for it. The card renders more than 60 frames per second, heating up only to 63 degrees with a consumption of 280 watts. It doesn't make sense to fine-tune it, but let's find some more demanding games. We will run our tests on a huge 32-inch MSI optics monitor with a resolution of 2560 x 1440 pixels, ideal for such a huge diagonal. Thus, the load on the video card is less and the pixel density is high enough, and there are no problems with the scale of the interface. An important feature of this monitor is the use of quantum dots, which are nanocrystals that are able to very accurately re-emit light to increase brightness. As a result, the monitor supports an honest HDR600, and photographers will definitely appreciate the 99% coverage of the Adobe RGB range. This is a 175Hz 10-bit IPS panel with a response time of 1 millisecond, G-Sync compatible. Other features include a USB-C port with a power delivery protocol, so you can charge your cell phone from it. And let's start our tests with Cyberpunk, which has finally updated to version 2.0. Recently, it was also patched to 2.01, where they fixed some issues with the translation into Ukrainian. But other than that, the story of Cyberpunk is now complete. Since we got an RTX 4080 and 2K resolution here, we safely set ultra graphic settings, reloaded ray tracing, and turn on frame generation with DLSS at quality. In this mode, the frame rate often flies up to as much as 100 FPS, but we are now more interested in the load it puts on the hardware. And here, not everything is perfect. On the one hand, the processor consumes 100 watts and is heated above 70 degrees, which is a bit much, but within the norm. But the video card showed itself in its best light. The energy-efficient Ada Lovelace architecture runs much cooler than the RTX 3000. Even in such harsh conditions, the 4080 doesn't reach its 320 watt limit, staying at above 280 watts when heated only slightly above 60 degrees, while also boosting over 2800 MHz. What other game can we use to give it a good load? Of course, the Last of Us PC port. Obviously, traveling the Earth after the fungus COVID pandemic can be done at ultra settings in 2K without any sorts of upscaling. In this scenario, the 4080 is capable of rendering more than 100 frames per second. At the same time, the load on it is less than in Cyberpunk, about 250 to 260 watts at 2800 MHz and a temperature of about 60 degrees. But it hurts the processor, 150 watts, heating at 80 degrees. But still, it keeps on going without dropping the frequency, maintaining above 5 GHz across the P cores. Modern Intel processors, and AMD for that matter, are notorious for producing a lot of heat. They even manage to do so in games. But there are two ways to cool them down. To begin with, let's try the simplest and roughest method that will work on all boards and at the same time will not affect the stability of operation in any way. We will simply lower the TDP of the processor so that it doesn't reach the wild 250 watts, which is what MSI actually did here by default. Launch into the BIOS, go to Advanced CPU Configuration under Overclocking in the case of MSI boards. Additionally, turn on Expert Mode, after which look for Power Limit Parameters 1 and 2. They may have different names such as short and long TDP, but you can easily spot them by values in watts. Let's talk a bit about how it works. Any modern Intel processor has two TDP values. Long duration power limit indicates the maximum CPU consumption at long-term operation, and short duration power limit at short peak loads. And the turbo time limit parameter is responsible for the time of such peak loads, and by default it is 28 or 48 seconds. After that time has passed, the processor returns to the level of the long-term TDP. Most boards manufacturers set the default values of TDP in accordance with Intel specifications, but MSI decided to distinguish themselves here. In our case, PL1 was 125 watts, which is standard, but PL2 was 190, while according to Intel's official website, it is supposed to be 253 watts. But I don't want to keep the processor locked behind the 125 watts, even in games it consumes about 150, therefore, if we assume that such a PC will be used only for gaming, it would make sense to limit the processor to 150 watts. This will reduce performance in productivity tasks, but it will also reduce heating. Let's try this in practice. In the hard 30-minute Cinebench R23 test, the processor now heats up only to 80 degrees, stopping at the specified 150 watts. No more heating to 100 degrees. At the same time, the frequency has decreased by only 300 or 400 MHz, which is less than 10%. This once again suggests that Intel is squeezing all the juices out of the silicon to compete with AMD without looking back at the insane heating. The heating of the VRM zone has also significantly decreased. If earlier the MOSFETs would heat up to 80 degrees, now they don't even reach 70. And the last pleasant cherry on the cake, the power drawn from the outlet has decreased by almost 100 watts, from 380 to 270. If we assume that the PC will work 4 hours a day, then in a year it will save almost 150 kilowatts. The CPU Z-test is short, but the processor still managed to drop frequencies. The result decreased by 10% to 11,100 points. Given that this is still better than most desktop CPUs on the market, such a loss of performance can be forgiven. In the Y-Cruncher test, the difference is only 6 seconds or about 8%. This is a very tough benchmark that makes the processor compute millions of byte digits, so without a TDP limit, our Core i7 quickly starts thermal throttling, which reduces the final difference with the limited CPU. As usual, the 3DMark gaming test for processors has shown the least of differences. Here, the 13700K with a TDP limit scored 1000 points or 5% less than the one at default settings. So, what's the result? The theory perfectly aligns with the practice. Limiting the processor from 250 to 150 watts affects performance in productivity tasks only a little, and with a noticeable gain in temperatures. The stability at the same time is not affected. The advantages are quite obvious. Now, let's see what happens if we pull the same trick with a video card. In our case, the RTX 4080 is doing well enough already. Even in hard tests, it doesn't reach its limit of 320 watts. And in games, it consumes about 250 at 60 degrees. But we still will demonstrate that even such an energy-efficient architecture as Ada Lovelace can still be improved. If you have an RTX series card, you don't even need any third-party tools. Just open the Experience overlay by pressing Alt-Z. Click on Performance, and voila, the fine-tuning options are right in front of you. All the cards will require a third-party tool, and the most popular utility is MSI Afterburner. The process is still very simple in both GeForce Experience and Afterburner. Just pull the power limit slider to the left. You will need to play around a bit to find the balance though. I decided to stop at 70%. In this case, the card will be able to consume only about 225 watts. Also note that this option will not affect the stability of your system in any way, since we do not touch either frequency or voltage. Such a seemingly huge reduction of power limit didn't affect the performance of our system in the superposition benchmark. The frame rate is still about 60, but the frequency was decreased a bit, from 2800 to 2600 MHz, which is about 7%. At the same time, the power consumption of the card dropped by 55 watts and the temperature by 7 degrees. In 3DMark, the performance loss is also around 7%. Is it a good exchange? I believe so. Now let's move on to video games. We'll also restrict the processor to 150 watts. Since it was enough for the default settings, it should also be more than enough with a power-limited GPU. Let's start with Cyberpunk again, but with the new ray tracing reloaded and at ultra graphic settings with frame generation and DLSS at quality. The final difference is only 6 frames per second or about 5%. The processor, as expected, is almost always working at the maximum 5.3 GHz, and the video card is working at the new TGP limit of 225 watts. This of course causes the frequency to drop, but only a bit, from 2800 to 2650 MHz. The power drawn from the outlet also drops quite a bit, from 530 to 430 watts. Play Cyberpunk like that for a year, and you will save enough in electricity bills to cover for the cost of the game. Next in line is The Last of Us. Here the processor often reaches the limit of 150 watts, but again, it doesn't throttle and the 5.3 GHz almost always holds. The 225 watt limit is a little bit too low for this GPU. It loses up to 100 MHz, which is less than 5% actually, but the temperature stays below 60 degrees. I think the conclusions are clear. Even such a crude method as reducing the TDP can make the system run cooler, more energy efficient, and quieter, with only a minimal impact on performance and even in some heavy workloads. But there is also a more subtle approach that can not only reduce heating but also increase the performance. It is called undervolting. And again, let's run through the basics. There is no perfect thing in our material world, and this also applies to processors and video chips. Therefore, manufacturers have to use averaged information, those values of frequencies and voltages at which most silicon dies will work stably. We talked about this in more detail in our video about binning. I recommend watching it. The basic idea is simple. You may well get lucky and your particular processor or video chip will be better than average, and therefore they will be able to reach higher frequencies in overclocking, or what is more important for us now, to keep the default frequencies at a lower voltage. And less voltage means less heating. Or if the limiter is the temperature, just like what we got, then at 100 degrees we'll be able to get higher frequencies. However, such magic, unlike simple reduction of power limit, has side effects. Firstly, not all boards allow tampering with the voltage. In the case of Intel, you normally need a solution on at least a B chipset. Secondly, since we're playing around with the voltages, this is equivalent to a game stability, so any changes will have to be carefully stress tested. Otherwise, don't act surprised when you get a blue screen of death. And thirdly, you may get unlucky and any decrease in voltage will lead to instability of the system. Alas, this is a silicon lottery here, and in it, as in any lottery, not everyone wins. But you can try. In the case of the processor, again, launch into the BIOS, find core voltage mode, select offset mode, and of course, select the minus. Now it only remains to set the value of this minus. It is individual for each processor, but in general, you can count on minus 150 to minus 50 millivolts for any CPU, even for Xeons. In our case, stable operation was achieved at minus 100 millivolts. On the Ryzen CPUs, undervolting is done a little differently. In the BIOS, you need to lower all core curve. You can learn about it in our review of the Ryzen 7600X. But when undervolting modern Intel processors, there's an important nuance which must be taken into account. They try to be stable always. With a significant voltage drop of minus 200 millivolts, our CPU loaded the system without any problems and even managed to run Cinebench, but the result was 2 times worse. And this despite the fact that all monitoring reports that there are no problems and the frequency is high enough. Therefore, when undervolting, it is necessary not just to run a stress test checking for OCCT errors and such for half an hour or so, but also monitor the benchmarks so that the results are at least at the default level. So what does the minus 100 millivolts give to our hot 16-core 13700K? At least the increase in performance and productivity workloads. In Cinebench, the processor scored 7% more points than under default settings, with no power limits. It scored 30,000 points. True, we're still running at 100 degrees, but the frequencies increased by 200 to 300 MHz, which gave a performance boost at the same power consumption. Therefore, the MOSFETs on the CPU power zone of the motherboard still have the same temperature, 80 degrees, just as before, and the computer draws the same amount of power from the outlet. There was no difference at all in the CPU-Z benchmark. This is easily explained by the fact that the test is short and the processor, even by default, doesn't have time to heat up to 100 degrees, and since there is no TDP limit, the frequencies are at max. There are no differences in 7-zip either. The test is not hard. The processor would boost to the maximum in this test even before undervolting, so here it only leads to a decrease in temperature. In Y Cruncher, the result has improved literally by a second. The processor still runs at 100 degrees, but now undervolting allows it to maintain the frequency of 200 to 300 MHz higher. In 3D Mark, the changes are also in the margin of error, since without undervolting, the processor would not overheat either and maintained the maximum 5.3 GHz. So what's the result? Undervolting the processor in our case didn't help to get rid of the 100 degrees of temperatures in heavy workloads, but at least allowed for a few percent improvement in test results. Not too great an achievement, but as I said, there is a lottery and a big dependence on the cooling system. Perhaps you will be a little luckier and the processor will become not just faster, but also cooler. Now let's move on to the video card. I will show you not only the 4080, which is already cool enough, but also the 3080 Ti, just to make it more visual. To do this, we need MSI Afterburner. In the program, you need to open the frequency and voltage curve editor by pressing Ctrl F. The main idea is to get frequencies similar to the default ones at a lower voltage. In the case of the RTX 4080, we see that the card is boosted to 2800 MHz at 1.1 volts. Therefore, you can try to lower this voltage to 1 volt or even a little more. For your particular card, you can find the best results online. Now we need to shift the curve to the left. It's easy to do. Take any point on it, hold shift and drag the entire curve right down. Now try finding the point with the desired voltage, in our case it is 975 millivolts, and raise it up to the level of the desired frequency. We have it at 2800 MHz. That's it. Now apply the settings in Afterburner and voila! A new curve should appear on the chart. However, it's not yet time to launch games and celebrate. To check the stability, you need to torture your video card in superposition for at least half an hour. And if there is no stability, then there are two ways. Either slightly increase the voltage or slightly lower the frequency. The first will obviously slightly increase the heating, and the second will reduce the performance. The choice is yours. Let's see what result the minus 125 millivolts undervolt has produced. In the superposition benchmark, the RTX 4080 lost only 50 MHz of frequency, but it became 4 degrees cooler and consumes 50 watts less. An excellent result. In 3D Mark, the difference is the margin of error, only a couple of percent. Now let's move on to video games. We will also leave the processor undervolted. We will check how this will affect its temperature and consumption. In Cyberpunk on ultra settings with reloaded ray tracing, frame generation and DLSS at quality, you can immediately see how much more efficient the processor has become. It lost as much as 20 watts of consumption, and this is a considerable 20%, which is why the temperature dropped from 7 to 9 degrees, without any impact on performance. The situation is similar with the video card. It lost only a couple of tens of megahertz of frequency, but also almost 70 watts of consumption. Looking at the temperature is a pleasure, only about 55 degrees. The final result of the benchmark is actually the same as default, the difference is in the margin of error. Given the fact that the system now pulls as much as 130 watts less from the outlet, there is no need to explain how useful undervolting is. Let's go further. The remake of The Last of Us. Do you remember how at ultra settings our Core i7 consumed up to 150 watts and heated up to 80 degrees? Forget about it. With undervolting, consumption dropped by as much as a quarter, and heating by an impressive 15 degrees. With the video card, the situation is even more visual. It consumes only 190 watts. This is less than that of the stock RTX 3060 Ti. That when the latter is more than 2 times slower. I believe this is quite a vivid demonstration of all the advantages undervolting can give. I will only add that reduction of heating will help your hardware last longer. But there is still one last unpleasant nuance. Even with the voltage reduced, our hot i7-13700K under a heavy load runs at 100 degrees. This problem can be solved without serious loss of performance by making a combo of the two methods explained. You can both limit the TDP of your processor as well as undervolt it at the same time. In this case, we will get both lower temperatures since the processor no longer consumes 250 watts and higher frequencies thanks to undervolting. Let's test it in practice by combining 150 watts with minus 100 millivolts. As a result, we get exactly the same temperatures in the long Cinebench test as with the simple limit of 150 watts. The heating of our VRM has not changed, the same 80 degrees, but the frequency has grown by a couple of hundred megahertz. As a result, the test performance is 5% higher compared to simply power limiting the processor, and 5% lower than with no limits whatsoever, and with a noticeable decrease in temperature and power consumption. In CPU-Z, the situation is similar. The result is exactly in between the one with power limit only and with no limits at all, the difference with which is now only about 6%. In Y-Cruncher, the same thing. Undervolting and a limit of 150 watts allowed it to win back a couple of seconds, so the difference with the default settings is about 5%. It is pointless to test such an undervolting combo in games. The processor doesn't consume 150 watts in them, so the result will be similar to the one obtained simply by reducing the voltage. Speaking of productivity workloads, however, this helps greatly. The performance loss is quite insignificant, but the benefit is definitely worth it. And just for comparison, let's try to reduce the appetites of my RTX 3080 Ti. In order not to stretch our already long enough video, I will combine all three tests into one. Of course, at first we will test the card at its default settings with its native TDP of 350 watts, then we will power limit it to 280 watts, and at the end, undervolt it, up to 1740 MHz at 800 mV. In Cyberpunk in 2K at ultra graphic settings with medium ray tracing under default TGP, we get 52 FPS. The GPU runs at 350 watts and its frequency is about 1800 MHz. The temperature we get is about 67 degrees, which is quite cool, but we can do better. Reducing TGP to 280 watts dropped the frequency by a couple of hundred MHz and the temperature by 4 degrees. As a result, the benchmark results dropped by only 8%. And this with a decrease in power consumption by as much as 70 watts. And at the end, undervolting. Now the card consumes 300 watts, but the frequency is only a couple dozen megahertz lower than the default 1800. Therefore, the result in the benchmark is at the same level. That is, we managed to reduce consumption by 15% and not lose performance. Why didn't Nvidia do this at the factory? Crypto miners do not need this, and the company didn't want to lose profit on discarding lower quality chips when one such cord would cost about $2,000 back in the days. Undervolting is power, overclocking is dead. At the beginning, the whole system would draw up to 700 watts from the wall, and at the end, less than 500. Almost 30% less power consumption with almost no loss of performance. All of this is because of the problems in developing new process nodes and the ongoing performance race. The chip makers squeeze the maximum out of their products already at the factory, at the cost of huge consumption and temperatures. And even the simplest reduction of the TDP of the processor or video card, available to absolutely all users, has a rather insignificant effect on performance, with a noticeable decrease in temperatures and consumption. And if in addition you spend an evening on undervolting, you can get a quiet and cool PC that will last longer and save a penny on electricity bills. And this is despite the fact that we decided not to dig even deeper into LLC correction and a more accurate way to set the frequencies and voltage curve in Afterburner, which can reduce power consumption even further. So overclocking is dead. Long live undervolting. My name is Mikhail Krashin. Stay safe. I'll see you again. Bye.